Alright, in this video we will be looking at um, derivatives. Basically, we will be fast forwarding from the first principles, which means we'll be looking at the rules that are derived from first principles that makes our life easier. But before we get to that, I've realized that most of the time learners, students fail to understand that the most important thing is algebra. Understanding algebra in the world of calculus is very important. So the first thing that we need to understand that when we introduce ourselves, having an intro here, when we introduce ourselves to derivatives, the first point that I noted is that you should make sure all your algebraic functions are written, sorry for the in, it's an error, are written in standard form of exponents. The following are the examples that I mean by saying that. Square roots and radical forms and other algebraic inverses. For an example, a square root of x is the same as x to exponent 1 over 2. Well, that is very important for one to know, and know that whenever you have to work with derivatives, you need to always convert your radical forms to exponent forms. And the other one is this one. It's very simple. From cube root of x squared, it will be 2 over 3 as an exponent. 1 over x is x to the exponent -1. 1 over x cubed is x to the exponent -3. We know that. 1 over square root of x, we can see that the steps there, you can first say square root of x to the exponent -1. Then you know that square root means 1 over 2. That means exponent multiply -1 by 1 over 2 be x to the exponent -1 over 2. Now, simplifying examples, given this sort of an example, you can be able to derive it using these simple rules. But the first thing you need to do is to check that it needs you to simplify first. To simplify it, it means you need to simplify factorize the above expression so that you can divide x minus 2 with x minus 2 and you get x plus 2. This one now, it's easier to derive if you were to use these basic rules. The second one here says that x cubed minus 7 over x. This can be partially written as x cubed over x minus 7 over x, which is equal to x squared minus 7 over x. But if you're given x over a denominator that has got more than one terms, that is not equal to, cannot be broken up in this way. That's one thing you need to note. You can pause this video and look at the slide as much as you want to look at it. NB, or note, you cannot derive if any of your functions are not written in the standard form of exponents. That we need to always remember. Right, now we get into the meta. Our meta here is rules of differentiations that we're going to use to derive. Now, the first rule, I call it, or we call it, the constant rule. The constant rule says that whenever you have got the derivative of the derivative of a constant that is the same as 0. We know that a constant can be any number from negative infinity to positive infinity, whichever number you can think of. Any number, 1 over 2, 2, -2, 5, square root of 2, square root of 3, square root of whatever, 5, pi, all sort of numbers we can think of. Any number we can think of that is a constant. Whenever I derive that, we get 0. The EGs are here, or the examples. When you derive 2, you always get 0. When you derive 5, that's the point. That's the main thing about this rule. The second rule we can talk about is called, the most important rule here is called the nth rule. Now, the nth rule says whenever you derive an expression with respect to x that has got an exponent n, you multiply the existing coefficient by n, and then you raise it to the exponent, the previous exponent, which was n, then you subtract 1, where n is also a constant. Then, as an example, we're having x to exponent 4. We multiply 4 by the existing coefficient, which was 1, which will be 4, then x cubed. Then this will be our derivative of x, 4. You can see that 4 now is our n. Now there, 4 minus 1 is 3. Number B, this one you may view it as a rule where the derivative of an x with respect to x is just 1, which is the same as dx over dx. That's just 1. I'm sorry, here it's supposed to be equal to, not multiplied by, it's supposed to be equal to 1. The third rule I can talk about now is when you have a function multiplied by a constant. The example that I have is that, or let's look at how we do it. When you have a c, which is a constant multiplied by a function, you take out the c as you just take it out. You put it out and you put it out of the derivative operation. Then we'll be left with the function. For an example, we're having derivative of 3x4. 3x to the exponent 4, we take out 3, we derive x to the exponent 4, then we multiply them together, we get that. Feel free to pause the slide, to pause this video so that you can look at it better. Let's move to the next slide. Now, we're looking at one of the most important rules as well, which is the sum rule. The sum rule does not necessarily mean that we will. Right. This one is called the sum rule. Remember, sum rule does not necessarily mean it will always be a plus sign. Hence, we put a plus or a minus. Now, in this rule, we'll be looking at a sum rule. Is a rule that combines all rules in either an equation or expression, which means all the other rules that we've been talking about, they can be all combined in sum rule, because sum rule encompasses all. Why do we say that? Because the sum rule says that the derivative of one function to the sum of another, we can call it f of x, g of x, can be, you can name it in anyhow. But then that when we answer our question, what we will do is to pull out our derivative operation as if it's a common factor, and we multiply it to f of x and derivative of to g of x. Then we'll have d dx of f of x, d dx of g of x. Then we have, there it is, d dx of f of x, d dx of g of x. Whether negative or positive, that does not matter. The sign does not matter. That's still summation. That's still sum rule. Continuing, like here it's been explained, it's like breaking a single function into multiple terms. Sorry, that's a bit of an error. It's into multiple terms, right? Suppose a function h of x is equals to 2x plus x minus 3. Then we say find dh of x dx. What we will do, we will break the function into 3 terms and we apply some rule. That is to say, we're going to say d dx of the whole function will be the same as d dx of 2x squared plus d dx of x minus d dx of 3. Now we start to understand what kind of functions are we having inside our h of x. Then we define them. After defining them, we need to understand which rules will we use. Now we get deep into it. We'll see that 2 and d dx of 2x squared, we will apply the rule where we have a constant and we take it out of the operation sign, then we derive what's inside. So you can see that we've got 2 d dx x squared. We take out 2, we take 2 outside of the operation, we'll be left with x squared to derive. Here, we don't have any constant. We can say it's 1, which is the same as leaving it as like just the way it is. We got to the other one here, we leave it as it is because it's the derivative of a constant. Now we continue to derive them. We can see that the derivative here will be, we apply the nth rule here. You can see that with the x to the exponent 2, we apply the nth rule. Applying the nth rule, we'll have 2 multiplying the existing coefficient, which is 1. We're going to have 2x, whereby exponent will be 2 minus 1, which will remain 1. X to the exponent 1 is the same as x. Now remember, the reason why I put a bracket is that this is our derivative where we put 2 outside. When we bring the 2 that we lost earlier on, we put it inside, it will give us 4x. Then 1 is the derivative of x with respect to x. Like we said, the derivative of x with respect to x will always be 1. Derivative of t with respect to t is always be 1. So the derivative of a constant, which is 3, will always be 0. And it's simplified to 4x plus 1. Right. In this slide, we will be looking at a conducive examples where we'll be trying to summarize we'll be summarizing what we've been doing, the rules that we've been having. So what we're going to do is that we're going to look at our question, which is say find ddx of 3x4 minus x square root of x plus 4 fourth root of x plus 5 over x exponent 5 minus square root of 2. We can identify them. The first one we can see it's going to require us to use the rule of taking out. The first thing we're gonna do here, we're gonna take out this constant. Let's not forget that we're gonna first start everything. We're gonna first start everything with what we call the sum rule, which means you're gonna apply ddx for every term in here. But let's not forget that when we derive certain expressions which have radical forms and other inverse forms which are not presented as in a way I can say in terms of exponents, we need to turn them to that. We need to convert them, or we need to write them in a way of exponents so that we can derive them easily. So we change that. We can see that this one is already in exponent form, is fine. This one is not, hence it's in red. This one is not, hence it's in red. This one also is not, hence it's in red. This one is a constant, it doesn't have a problem, we can derive it as it is. Then before we derive, we need to change this, which means you're going to simplify. X over square root of x, it is the same as having x to the exponent 1 over x to the exponent 1 over 2. You put down the base, you take the exponent of the numerator, you subtract the exponent of the denominator, and we end up having x to the exponent 1 over 2. And here we end up having exponent 1 over 4, where our constant remained 4. Here, same thing happens here, whereby now it changes to -5 because it's what you call a division, a quotient. Now this will still remain a constant. We continue now to apply our sum rule, our beautiful sum rule. We're now going to put the dx into each and every term. We can see dx, 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 dx. That's the sum rule. We are now applying our operation sign into each and every term that there is in our function. Now we start to apply here where we have a function and a constant, we take out a constant. This one here doesn't have a constant, we leave it as it is. This one here has that 4 as a constant, we take it out. Here you can see this one as well, we take out 5. As you can see, this one remains, it's a constant. Now we continue. Finally, we're gonna derive. Here we derive, here we can see we derive 4. We multiply 4 with the existing coefficient, we'll have 4x cubed, whereby 4 minus 1 is 3. That's true. There we have our derivative in here multiplied by its constant. Now minus, we derive 1 over 2 multiplied by existing coefficient, which is -1, then will be -1 over 2. Then now the exponent will be 1 over 2 minus 1, -1 over 2, like that. Now we can see as well again here, we're having 1 over 4 multiplies the existing coefficient here, which is 1. Now it comes 1 over 4, and then we're going to multiply by 4. Exponent will be -3 over 4, which is 1 over 4 minus 1. Here will be, we take out 5 there, and we have it, then we remain with -5. -5 minus 1 is -6. We have -6. Then here we have x. We multiply by the coefficient will be 5, but then we know the derivative of a constant, which is square root of 2, which will be 0. Now the final answer will be 12x cubed minus 1 over 2 square root of x plus 4th root of x cubed plus 5 over 6. Now let's move on. Now this is an activity or exercises that I need you to try to attempt, which I'll also try to make some answers in upcoming videos, which I think they're very simple, as we can see. They're very simple. Here you will apply some rule, and then you write these things in exponential forms. You write them in terms of exponents. And this one here, it will be derived with respect to t. It's no longer x. You must be aware of that. Now this one here is fine. This one here, you'll need to change it, and I'm writing in a form where t is expressed as exponents only, no quotient. Now this is a constant. You do what you gotta do. Here you have this one, then find f of d of dx of f of x over g of x. You simplify, you derive. Here now, this one, you need to change this one, and the final one as well, you need to simplify it by factorizing the top fraction, and then you can find your derivative. Now this is what I had for you in this video. See you in the next video.